Hello, let's talk about math again. I will be speaking English today because most of my math friends don't understand German, and I'm going to talk about my research today, so I think it makes more sense for me to speak in English. I apologize for the language mistakes that I will make, and I apologize for my charming German accent, but I will try as best as I can. The thing is, I got invited to give a talk in Halle an der Saale in a week. And I will just give this talk here now. It's about the setup of my research, if we want to be more exact. It's about how we can view buildings as generalizations of projective spaces and about the Moufang property. I'm a first year PhD student in mathematics, interested in geometric group theory and buildings. And I think this video should be accessible for master students in mathematics or like advanced bachelor students, but keep in mind this is not a video that just anyone can understand. When I talk about buildings, it's not about architecture. I will not speak about architecture, I will speak about math, and I will speak about advanced math. Even though I'm a PhD student in mathematics, and even though I will be talking about my research interest, it is of course still possible that I make some mistakes. I hope I will not make mistakes, but it is of course possible. So if you notice any mistake, please let me know, and then I can pin a comment or write something in the description and make a correction. Before I start talking about the mathematical content, I want to make one historical remark. So today we will be talking about the Moufang property. The Moufang property is named after Ruth Moufang. Ruth Moufang was a woman in math, and she was actually the first woman in math who ever got a proper position as a professor in Germany. Before her there was Emmy Noether. Emmy Noether was also a woman in math who worked in math and also did some teaching, but Emmy Noether actually never got a proper position as a professor. So Ruth Moufang was actually the first woman in math in Germany who ever got a proper position as a professor. And that's my historical remark. Regarding the structure of the video, first I will be talking about Coxeter groups. I also have a dedicated video about Coxeter groups if you want to know more. Then we will talk about buildings. Also have a dedicated video about buildings if you want to know more. And then we will talk about buildings as generalizations of projective spaces. This will be the main point of the video. And also we will mention the Moufang property and why it is relevant to buildings. And then we will try to see how we can visualize the Moufang property and get an understanding about what it is and what it does. So the goal of this video is actually to get to this picture. This picture is the visualization of the Moufang property, and if we can understand how it is relevant and how we can see this picture in a building, then the goal of the video is achieved. So why are we even interested in the Moufang property? The thing is, given a building, and if you don't know what this is yet, I will explain later, just think of a geometrical object. Given a building, we have no idea if nice automorphisms exist. Buildings are relevant in many different mathematical fields, and sometimes what you really need in order to work with a mathematical object is to know that automorphisms exist. And the Moufang property gives us the existence of very nice automorphisms, and that makes it nicer to work with buildings in general. Furthermore, there's a very nice theorem by Tits that we will also talk about that says that all thick irreducible spherical buildings of rank at least 3 have the Moufang property, and that actually generalizes the fundamental theorem of projective geometry because buildings are generalizations of projective spaces. Not important to understand right now, but I think it's very cool that we have a generalization of the fundamental theorem of projective geometry. Another theorem tells us that given a Moufang building, if we look at the automorphism group of the building and then look at certain subgroups of this automorphism group, we already know that they are simple groups, which is quite strong. One other nice thing is that Moufang buildings are classified, so we actually know exactly what they are. So now that we are all motivated, know the goal, know the structure, let's start with Coxeter groups, because Coxeter groups are relevant for all the following definitions that we need. So let I be an index set. A Coxeter matrix is a symmetric array with ones on the diagonal, and all other entries are natural numbers greater or equal to or infinity. So basically a Coxeter matrix always looks somewhat like this. Given a Coxeter matrix, we can always draw a Coxeter diagram. We do that by drawing a vertex for every element I in the index set I, and drawing edges between two elements I and j in I if mij, the entry in the Coxeter matrix, is greater than 2, and we label that edge by mij if mij is greater than 3. So for example, given a 2 times 2 matrix, we draw 2 vertices, and if the other entries that are not on the diagonal are 3, we draw an edge between the 2 vertices. If it is greater than 3, we also draw an edge and we label that edge. So you can see it in the pictures. Given a Coxeter matrix or a Coxeter diagram, we can define a Coxeter group. So let's say our index set is still called I, and let's say our Coxeter diagram is called gamma. Then our Coxeter group of type gamma is the group with generating set I, and as relations we want to have that ij to the power of mij equals 1 for all ij in I, where mij is not infinity. Sometimes when you have a Coxeter group W with index set I, you can also see these tuples wi, and this is just called a Coxeter system. The W just stands for the Coxeter group and the I just stands for the generating set of the Coxeter group. Let's look at an example. Let's look at the 2 times 2 matrix again with 1s on the diagonal and 3s in the other entries. We can see that we have 2 different elements in our generating set. Let's call them G and H. And we can see that GH to the power of 3 has to equal 1. We can see that GG to the power of 1 has to equal 1, so G square is 1 and H square is 1, and I say 1 for the identity. So we can write down all of the group elements that we can get. It's the identity is GH, GH, HG, HGH, and HGH is the same as GHG. So we just get the dihedral group D3, sometimes also denoted by D6 as preference, but it's the symmetry group of a regular hexagon. In general, dihedral groups are the symmetry groups of the regular polygons, and Coxeter groups are generalizations of dihedral groups and include the symmetry groups of the Platonic solids. So now that we know what a Coxeter group is, let's take a look at buildings. I will give a rough definition first, then we will look at some examples, try to get the idea and try to get an intuition about what a building might be. Then I will give the exact definition. However, for this talk, it's not that important that you understand all the details of the exact definition. I will give it though, but let's have a rough definition first. Suppose we have a Coxeter system Wi of type gamma. Then a building big delta of type gamma is an edge-colored graph together with a map little delta from big delta times big delta to W that measures distances in the graph. And we will see what that means. We also need some other properties in order to really have a building, but these are more technical details that we don't necessarily need right now. The idea is that we have an edge-colored graph and the edges are colored by the elements of the index set, and when we walk a minimal path in our graph, then we get a reduced word in the Coxeter group, and when we then take the word length of that reduced word, we get a distance in our graph. So that's the idea. I will now show you a picture of an edge-colored graph that has all the properties that you need in order to have a building. So what you can see here is a building, and if you watched my video about buildings, you've already seen this example. In the other video I talk in length about how to construct this graph, how to get this, where this example comes from. That's not important right now. Let's just appreciate the picture for a moment. Looking at the graph, we can see that we have 2 different colors, purple and green. That means that in our Coxeter group we want to have 2 elements in our generating set. Then next we can look at the maximal length a minimal path in the graph can have. So what is the maximal distance of 2 elements in the graph? And I marked 2 vertices that have a maximal distance in this graph, and we can see that we can either walk purple, green, purple or green, purple, green. This should be the same then. So the maximal length of a minimal gallery is 3, and we see that if we say that green is our generator J and purple is our generator H, then we have GHG equals HGH. So we actually arrive at the same Coxeter group, D3, that we already looked at. So I hope this gives a rough idea what a building is and how it all works and fits together with the map and the graph. And now I want to talk about another concept that we will need for our exact definition of a building, and that's the concept of a residue. So as we have seen later, our index at I should correspond to the set of all colors of our edge-colored graph. So now imagine we have an edge-colored graph, and imagine we have a set I, that is our set of colors, and now we only want to look at a certain color in our graph. So let's say we pick out a color I, and we discard all the edges whose color is not this color I. Then we get a subgraph, and now one connected component of this subgraph is called an I residue. It's also way easier to understand that with pictures. So let's take a look at our graph again, our example that we've already seen. And now we want to know what the purple residues are. So we discard all the edges whose color is not purple. So we discard all the green edges, and then we get a subgraph with all the purple edges. And now every single connected component is a purple residue. So we get these triangles, and one triangle is one purple residue, and in total we get 7 purple residues. On the other hand, we can also discard all the purple edges, and then we can get 7 green triangles, so 7 green residues. So that's the idea of a residue. Now to our exact definition of a building. Like I said, it's not important right now that you understand all the details of this definition. It will not be important in the following, but I wanted to give the exact definition anyway. So suppose we have a Coxeter system Wi of type gamma, then a building big delta of type gamma is an edge-colored graph together with a map small delta from big delta times big delta to W, such that every I residue is a complete graph with at least 2 vertices, and if we have minimal paths in our graph, then this corresponds to a reduced word in our Coxeter group, and that means that we get some kind of distance function. So our distance is a word in the Coxeter group. Minimal paths in the graph correspond to reduced words in our Coxeter group. And that is the main point, main idea of a building. Of course, after seeing the exact definition, we will look at examples again. The one example we've already seen a lot, it's our edge-colored graph with the green and purple edges. And as we've seen, for no matter what color we pick, we get triangles as residues. So in particular, we get complete graphs with at least 2 vertices. We can also look at the hexagon, which is actually the Cayley graph of D3. And this is also a building. We can, if we associate orange with the generator G and pink with the generator H, we can see that our minimal path in the graph correspond to reduced words in our dihedral group D3. And if we look at the residues, for example, we can look at all the orange residues, then we get 3 orange lines with 2 vertices each, and these are complete graphs, and we have at least 2 vertices, and same thing for pink, so we can see that this is also a building. Now to 3 important adjectives in the context of buildings. First of all, a building is called spherical if the corresponding Coxeter group is finite. Easy definition, but why the word spherical? That is a little bit more complicated. It is the case that building blocks of a building are called apartments, and you can show that these are exactly the Cayley graphs of the Coxeter systems of the same type as the building. Now, if the Coxeter group is finite, these Cayley graphs are triangulated spheres, and that's why we then call the building spherical. You can read more about that on page 115 in the Abramenko Brown book about buildings. It's not important to understand that right now at all, we don't need it, but I wanted to give a rough idea why the word spherical is used here. Only important thing for this talk is that a building is spherical if the corresponding Coxeter group is finite. A building is called irreducible if the corresponding Coxeter diagram is connected. Also easy definition, not much going on there. Then a building is called thick if for every I in our index set I, the I residues have at least 3 vertices. So we have seen in our definition of a building that the I residues need at least 2 vertices, but if they have at least 3, then our building is called thick. Okay, let's look at our examples again and see which adjectives fit. So with our big graph with the green and purple edges, I've already mentioned it a little bit. The corresponding Coxeter group is also the dihedral group D3. So we have a Coxeter diagram with 2 vertices and an edge between them. So in particular, this is connected. So our building is irreducible. We've also seen that the dihedral group D3 has 6 elements. So in particular, it is finite. So that means that our building is spherical. We've also seen that our residues are triangles. So we have 3 vertices in each residue, and that means our building is thick. Now let's look at our hexagon with the pink and orange edges. It is the calligraph of the dihedral group D3. The corresponding Coxeter group is D3. That means we get the same Coxeter diagram with 2 vertices and an edge. So this is also an example of an irreducible building. It is an example of a spherical building, but as we've seen, the residues, the I residues, are just aligned with 2 points. So 2 vertices, which is not greater equal 3. So this is not a thick building. This is actually an example for what we would call a thin building. But yeah, so this is not thick. Fun fact regarding that, if we have a Coxeter system Wi, then the calligraph of W with respect to the generating set I is always a building and is always a thin building, and the thin buildings are up to isomorphism exactly the calligraphs of Coxeter groups. So that's interesting. I briefly mentioned the word apartment before, and now we will actually see what it means. If we have a Coxeter system Wi of type gamma and we have a building of type gamma, then the apartments of that building are exactly the calligraphs of the Coxeter group W with respect to the generating set I. And these are the thin buildings of type gamma, and we can find them in our maybe larger buildings. So these are the apartments, and we can always find apartments in our buildings. And yeah, so that's what I meant with our building has these building blocks which are apartments. So calligraphs of Coxeter groups are exactly the thin buildings. And if we have a thick building of the same type, we can find these calligraphs in our thick building. That's the point. So I mentioned at the very beginning of this video that we are interested in the Moufang property because it gives us very nice automorphisms. So the next question is, which kind of buildings have the Moufang property? And Jacques Tits did a lot of research about that. And we have a very nice theorem by Tits that says that all thick irreducible spherical buildings of rank at least 3 have the Moufang property. So in 1974, Tits wrote a paper called Buildings of Spherical Type and Finite Bien Pairs, and in that paper he classified all thick irreducible spherical buildings of rank at least 3, and at the very end of this paper, in an addenda, he mentions the Moufang property and says that it's kind of obvious that all the buildings he has just classified have the Moufang property. And he also mentions that the Moufang property could be used to also classify the rank 2 buildings. He did not give proofs for that, but in 1977 he gave the proof for the statement that all thick irreducible spherical buildings of rank at least 3 have the Moufang property. And then in 2002, together with Richard Weiss, he also did the classification for the rank 2 case. So if you have a building and you assume it is Moufang and it is thick, irreducible, spherical and has rank at least 2, then you can classify. So for the rank 2 case, you have to have that the building is Moufang in order to classify. But yeah, that is the historical context around that. So if you want to know more and want to know about some literature, you can of course read just the lecture notes and papers of Jacques Tits, especially Buildings of Spherical Type and Finite Bien Pairs, or it's in German, Endliche Spiegelungsgruppen, die als Weylgruppen auftreten. You can also read the book Moufang Polygons by Jacques Tits and Richard Weiss. Richard Weiss also wrote a very nice book called The Structure of Spherical Buildings that kind of is, I think, beginner friendly. and it gives you, first of all, it spends a lot of time to get to the definition of a building, and then it explains the Moufang property and all that stuff. So it's a very nice book, and I recommend it very much if you want to know more about that. You can also, of course, there's something written about all of this in Abramenko Buildings. And you can also, so if you're more interested in incidence geometry and buildings as generalizations of projective spaces and stuff, or just learning about incidence geometry, I find the book Points and Lines by Shult very beginner friendly, and I can recommend it very much. At this point, you might be wondering, we have said why the Moufang property is amazing. We have seen which kind of buildings have the Moufang property. But what is the Moufang property? We did not even define it yet. The thing is, the definition, the usual definition of the Moufang property is quite complicated. It's a lot of text. And we have not even given all the necessary definitions to understand this whole text yet. So we will not talk about the usual definition of the Moufang property. What we want to do next is view buildings as generalizations of projective spaces, and then define what it means that a projective plane has the Moufang property, and see how this helps us with buildings and how we can visualize it then. It will be way easier, it will be so much nicer, I promise, and we can still understand the Moufang property without talking about this usual definition that you see in books. So I told you that thick irreducible spherical buildings of rank at least 3 are classified, and we can classify them using the Coxeter diagrams. So it is actually the case that buildings of type AN correspond to projective spaces, buildings of type CN correspond to polar spaces. I will not give the whole list, but like they are classified and you get a list like this. And so now you can already kind of see that buildings are generalizations of projective spaces, because projective spaces are there as in corresponding to AN, but there are also different kinds of buildings, so it's a generalization. And that is now why we want to talk about projective spaces and try to understand them, and then see how we can get to buildings and the Moufang property. In order to understand what a projective space is, we have to understand incidence structures first. And then I actually want to define projective planes, because these are the easiest examples of projective spaces, and after that we define a projective space. So an incidence structure consists of a set of points, a set of lines, and an incidence relation. Incidence relation means something that tells us if a point is living on a line or not. So we say that we have a set I, which is called the incidence relation, and it is a subset of the set of points times the set of lines. So if a tuple of a point and a line is an I, then that means that the point lies on that line. And the elements of this incidence relation I, so the tuples with point and line, we also call them flags. Now, a projective plane is an incidence structure such that we always find connecting lines between 2 points. Every 2 lines intersect in an intersection point, and a quadrangle exists. That means that we have at least 4 points, and no matter which 3 points of this quadrangle we look at, they are never collinear. So we have at least 4 points, of which 3 are never collinear, which means they are not on a lined together. So an example for a projective plane would be this picture. It's the Fano plane. I colored the edges not because we want to talk about edge coloring or anything like that. I only colored them to make it very clear that we have 7 different lines here and what they are and where they all intersect. So the one circle in the middle is actually 1 line. And now you can check very easily that we always have connecting lines between 2 points. We always have that 2 lines intersect, and we can actually find a quadrangle in our picture. It is the case that we can view the Fano plane as a graph. And for a building, we always have a graph and we have a distance function. So now the next question would be, how could we define a distance function for a projective plane? And that's a bit tricky, but we can do it. So imagine we have two flags. So we have a point P and a line L here, and then we have a point P prime and a line L prime here. And now we want to measure the distance between these two flags. So what we can do, we know that two lines always intersect. So we know that L and L prime have an intersection point. So we can go from this flag to the next flag by changing P for the intersection point of L and L prime. Then from there we can change our line and go to a flag that has the intersection point and then the line L prime. And from there we can go to our flag we wanted to go to is the P prime L prime flag. So if we now say that if we change the point, that should correspond to G, and if we change the line, that should correspond to H, we can get a distance GHG between these two flags. What we could also do is, we have these two flags, and we know that between 2 points we always find a connecting line. So there's a connecting line between P and P prime. So from this flag we can go to P and then the connecting line P, P prime. And then from there we could go to P prime, P, P prime, and then we can arrive at our flag P prime, L prime. So this would also be another option, and then we would get HJH as the distance. Of course, if the two flags are already the same, then we have distance identity, which then corresponds to 0 distance. And if we don't have to change so much around because the flags already have a line in common or a point in common, then we of course get the word with less word length. So we can write that down in a table, and if you want you can check the other cases or just think about them a little bit more. But this is basically how we get a distance function for projective planes. This is exactly what happens. So just to catch up, projective planes are examples for projective spaces. We will define projective spaces next. Buildings of type AN correspond to projective spaces. We've now talked about projective planes, which are examples for projective spaces. And now buildings are generalizations of projective spaces, and this is our trajectory. So a projective space is an incidence structure such that we always find connecting lines between 2 points. Every line has at least 3 points, and if we have 4 different points, A, B, C and D, and we have that the connecting lines A, B and C, D intersect, then also A, D and B, C should intersect. And this last thing is also called the Veblen-Young axiom, and we can visualize it in a little picture. We can see that these 2 lines, A, B and C, D intersect. So we already know that we need these other lines that also have to intersect because of this axiom. So what would be an example for a projective space? This picture. It is drawn by Franz Marcelis. Don't know how to pronounce the name, but you can also find it on his webpage. And I think this is a very cool example because you can actually find the Fano planes in this example. So if you have a projective space of higher dimension, you obviously have projective planes in the space. So I think this is cool because you have this 3-dimensional little drawing and then you can see the Fano planes in there. So one can check that this is a projective space. I will not do that now, but this would be an example. Next, I have a little proposition that I will not prove. But in projective geometry there are some theorems called structure theorems, and they basically tell you a little bit what a projective space can be. It can either be trivial, so consisting of just 1 point, or consisting of just 1 line with 3 points, or it can be a projective plane. We already talked about that. So for us the most interesting case is the third case, which is a projective space can also be some PG VK for V a vector space and K is Q field. So if you have a vector space V of a skew field K, then you can define the set of points as the set of one-dimensional subspaces of V and the set of lines as the set of two-dimensional subspaces of V. And with that you can get a projective space. Suppose we are in the case that our projective space is some PGVK for V an n+1 dimensional vector space. Then our flags are actually not just point and line, but more than that. Consider the set of all proper non-trivial subspaces of V. Then we get a partial ordering of that set by inclusion. And now our flags are actually increasing sequences of these subspaces. So we have some subspace U1 that sits in a subspace U2, etc. And the maximal length we can get is n, if we have an n+1 dimensional vector space. So these are actually our flags. The maximal length a flag can have is n, and these maximal flags are very important. Now we want to find a distance function for these flags. And there's actually a theorem that I will unfortunately also not prove that basically gives us this distance function. If you're interested in the proof, you can find it in the small buildings books by Brown on page 84. Like I said, I will not prove it, I will state the theorem next, but it gives us the distance function. Given an n+1 dimensional vector space V over some k, consider two maximal flags U and W. We will write U as U1 ... UN and W as W1 ... WN. Now the theorem tells us that there exists a basis B, write it as B1 ... Bn+1, and a permutation pi in the symmetric group sim n+1, such that we can write every subspace of the flag U, let's say Uy, as generated by B1 ... Bi. And we can write every subspace Wi as generated by B pi of 1 ... B pi of I. And this works for every I between 1 and n+1. And this permutation is unique and independent of the choice of B. And that is the thing that the theorem tells us. This is obviously something one would have to think about and one would have to prove. I told you where to find the proof. But with the theorem now we can define our distance function little delta as just this permutation. So the distance between two of these flags should just be pi. And this is what works for us. And now we have a distance function on our projective spaces. Now I will define another word. Let S be a projective space of dimension n. Then we call the n-1 dimensional subspaces hyperplanes. So in particular, in the example of the projective space we have seen, the hyperplanes would just be the projective planes, the boundary planes. So if we have a three-dimensional projective space, the hyperplanes are always the projective planes. And if we were in a projective plane, then the hyperspaces would be lines. And now we finally get to talk about automorphisms. So let S be a projective space, H a hyperplane in the projective space, Z a point in the projective space. Then an automorphism from S to S has axis H if it fixes H pointwise, and it has center Z if it fixes every line through that line-wise. This is again easier to understand with the picture. So suppose we are in a plane, then our hyperplanes are lines. Let's pick a line H, and this line has to be fixed pointwise. Then let's also pick a point as a center. In general, the center does not have to lie on the hyperplane, but let's say our center is just in the middle of that line, and we call the center Z. So now every line through Z has to be fixed line-wise. It has not have to be fixed point-wise, that is important, but line-wise. So for example, if we look at this picture and we rotate it around 180 degrees, then we see that the axis is fixed pointwise and every line through the center is fixed line-wise but not point-wise. So this would be an example of an automorphism with axis H and center Z. And now we can define the Moufang property for projective spaces. A projective space S has the Moufang property if for each pair HZ, H being a hyperplane, Z being a point, where Z is lying on H, the group of automorphisms with axis H and center Z acts transitively on the fixed lines through Z. So if we now want to visualize that, we can go back to our simplest examples, which are projective planes, and we get to exactly the picture I showed you at the very beginning of the video. So if we are in a projective plane, for each pair of a line and a point on that line, we want to find automorphisms so that the line gets fixed pointwise and every line through the point gets fixed line-wise, but also such that we have transitivity on the points through the fixed lines. So that is the Moufang property for projective planes. So if you want to show that a projective plane in a projective space has the Moufang property, you have to find or construct these nice automorphisms. And for that you can just take an arbitrary pair of a line and a point, with the point lying on that line, and then you pick two arbitrary points on an arbitrary line through that point, and try to find an automorphism that moves the one point to the other point, fixes every point through the line pointwise and every line through the point on the line linewise. And if you can do that with just arbitrary lines and points, then you know that you can always find such automorphisms, and then you get the Moufang property. And that is actually exactly what I try to do in my research. In my research I view buildings as generalizations of projective spaces and use pictures like this in order to try to construct these nice automorphisms, and then the end goal is to find an alternative proof for Tits' theorem that all thick irreducible spherical buildings of rank at least 3 have the Moufang property. So now you know what I'm up to. Thank you very much for watching until this point. If you liked the video, you can actually like the video. You can also subscribe, or if you want, you can send me money via PayPal or Ko-fi or become a Patreon. You don't have to, but it's a possibility. Yeah, thank you very much for listening, and goodbye.